Hello and welcome to the second lecture on Hamiltonian paths. We're actually going to have a much shorter portion of this. We're going to run through a couple of reminders and leave it at that. Really what you learned about Hamiltonian paths yesterday was the bulk of the material for this time. Later on we'll get into working with directed vertex edge graphs where we'll have a certain direction that an edge can take, meaning it can't go backwards, and that really starts to mess with things. But so what I wanted to do right now is I just wanted us to take a look at this graph. Now, this graph is a very, very basic one. Obviously, we see that not all of the vertices are connected to all the other ones. So if I want to go through and I want to create a path, and you'll notice that I'm using the term path as opposed to circuit. So that means that I'm going to start in one spot and I'm going to move through, and I just need to make sure that I touch all the vertices once. I don't have to come back to my original space. So let's just kind of take a look at one. Let's say I start at A. I'm going to go to F, to E, to D, to B, and then to C. Okay. Now, that is a path. And it's important to note that if I go in and take a look at this path, I could actually go through and make this a circuit. Okay. I could take this and I could connect it over, and I can be good. Okay. Now, let's say that I wanted to come up with another one. So let's start anywhere else, and we're going to kind of just walk through this. We're going to go from D to C. There we go. And then up to B. And from there we're going to go to F. And then to E. And at this point we should notice we will run into a problem. We really want to get to A, but if we go up to D, now we're going to have to go back through and find a path such that we're going to have to come back to B. Right? So a lot of times when we're doing these Hamiltonian paths, there's a lot of trial and error involved. We're really using that concept of the nearest neighbor, and we're trying to really just get from one place to the next. Okay? So let's try this again. And a lot of times when we do this, we don't actually have to reinvent the wheel. We can actually just use what we've already done, but just a little differently. Case in point, we're going to go from D to C, to B, and then back to A, and from here, we go to F, and then to E. So, we take a look at this. We've got D to C, to B, to A, to F, to E. Okay. Now, as we look here, as we take a look at what it is that we're doing, we're just creating paths. We're not doing anything exciting here. We're not doing anything monumental. Okay. Now, let's think about what these two paths are. Okay. Let's write these out so we have them. Okay. We've got A, F, E, D, B, C. And we've got D, C, B, A, F, E. Now, because we're working with paths and we're working with a system that does not have a direction to it, again, meaning that all the paths can either be gone down one way and the opposite way, we have a path that goes this direction and this direction. Right? So we have actually two viable options out of this. Okay. Now, I'm going to take these. And we're going to put these on the next page. Right? And The reason we're going to do that is we're going to take this graph and we're going to do some assessment of which path is better. Okay? Now, it depends on how we're setting this up, but what we want to think about is how we can actually make some sort of assessment of a better path. In this case, I'm going to say that the weight of each path gives us some sort of efficiency. And of course, when we're dealing with efficiency, we want to make that number as small as possible. Okay? So, even though these are both good paths, we want to figure out which one's better. So, I'm going to go in and add up all of these weights. Okay? Let's take a look at the first one. Okay, if I add that up, I've got 8 plus 12, which is 20, plus 17, which is 37, plus 12, which is 49, plus 15, which is 64. So that has a weight of 64. Okay. Let's take a look at the next one. So I've got from D to C, which is 13, and up to B, which is another 15, so now I'm at 28, over to 10, now I'm at 38, down to F, so 38 plus 8 is 46, and over to E, we're now at 58. So this one gives me an efficiency of 58. So, in this case, I said that my weighting was an efficiency, so I wanted to make that number small as possible. So this is the better of the two. Okay? If this were different, if I wanted to make that number as big as possible, of course I would go with the bigger number. Now, you're going to use this information to cover and discuss one of the most famous Hamiltonian path problems, which is the traveling salesman problem. You have a worksheet that covers that. Make sure you start at the beginning and walk through it step by step. It is a very, very famous problem and a very, very good one, a very, very interesting one. And with that, I will tell you to have a good rest of the day.